4.3, probability applications of counting principles. We start with a concept that you should know. Probability is part over total. It's always going to be part over total, so don't forget that. We've been counting. Counting was finding how many ways there were, but probability is part over total. We know that and usually means we're going to have to multiply, or usually means we're going to have to add, so keep that in mind. Now, this flow chart, I want you to use this flow chart when you get stuck. All right. If you know what to do, just do what you do. But if you're stuck, then ask yourself this set of questions. All right. When you look at a problem and you don't know what to do, ask yourself, is this a group from a larger group? We've kind of already been doing that, but yes or no. If it's not, then it's probably going to be a fundamental counting principle. And remember, that's the blanks problems like this. But if it is a group from a larger group, you have to ask yourself a second question: does order matter? And if it does, then it's permutations. And if it does not, then it's combinations. I think that's a useful way to figure out what type of problem it is if you're stuck. So when you're stuck, if you're stuck, go back to that. Number one, Johnny grabbed a handful of 5 marbles from the jar. See that picture of the jar? How many ways are there to do that? So first question I would ask is, am I taking a group out of a group? All right, I am. I'm taking 5 out of however many marbles there are. It turns out that there are 20 marbles in this jar. I'm taking 5 of those. How many ways are there to do that? Well, it's going to be 5 out of 20, right? Does order matter? Does it matter which one I pick out first? Does not matter, so that's a combination. 20, choose 5. 15,504. Now notice, that is not a probability question. That is a counting question. How many ways are there to do such and such? That's not probability. That's counting. Part B is probability. Find the probability that all 5 marbles are black. So I'm finding the probability that all 5 of them are black. And so when we talk about probability, we know it's part over total. And so really what I'm looking at is the number of ways to get 5 black ones out of the number of total possible ways in this scenario. So it's part over total. Remember back from last unit when we talked about sets, that in just meant how many ways, how many things are there. So part over total, basically I want 5 black ones. So go back to that flow chart. 5 black ones, is that a group from a group? Yeah, 5 black ones out of how many black ones? There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 black ones. So I want 5 blacks out of 10 blacks. That's a group from a group. Does order matter? No. So that numerator is going to be 10, choose 5. Now the denominator, I want 5 total marbles out of 20 total marbles. Well, I already did that. 20, choose 5 was 15,504 just a second ago. But now the numerator is 10, choose 5. 252. As far as reducing fractions, usually I'll only want to reduce fractions if it's something that's easy. If it's an easy fraction to reduce, do it. If it's not, then use your calculator. It's going to be 252 divided by 15,504. I usually will like decimals rounded to 4 decimal places, 0.0163. If you don't know what to round it to, keep 4. Part C says find the probability of grabbing 3 striped and 2 white. So remember, when you see this word and, a lot of the times and is going to mean times. So 3 striped and 2 white. So 3 stripes and 2 white. Think about it as times. All right? Times. I want 3 stripes, but 3 stripes out of how many stripes? 6. So I've got 6, and I'm going to choose 3 because order doesn't matter. I want 3 stripes out of the 6 stripes. And I want 2 white. Group from a group. It's 2 whites out of 4 whites. Order doesn't matter. That's how many ways of doing what I want to do. But since this is a probability question, probability is part over total. Well, that total is still the same thing. I've got 5 marbles out of 20 marbles. And so 6, choose 3 is 20, and 4, choose 2 is 6. You start seeing the same numbers over and over again. 4, choose 2, you'll remember that's 6 at some point. But I've got 20 times 6 over 15,504. Or 20 times 6 is 120 divided by 15,504. 0.0077. Number 2, Lori Hales is one of a group of 22 nurses. 4 nurses are to be downsized. In how many ways can this be done? So that first question is not probability, it's a counting question. In how many ways? So think about it. Am I taking a group out of a group? I'm trying to pick 4 nurses out of how many nurses? So 4 nurses are going to get called into the office and fired. Does it matter who comes in first? I don't think so. That's 22, choose 4. (7315). B, find the probability that Lori Hales will be among the 4 downsized. All right, so some of these problems you have to really think about. You have to think about what they're really saying. So find the probability that Lori Hales will be among the 4 downsized. So when they say Lori will be among the 4, what they're really saying is Lori, and what's the implication? Who's getting fired? Lori and 3 others. Very good. And so I think it's really powerful if you can think of the problem in this way, because we can keep going back to the same well of, I know and means times, so it's going to be a multiplication problem, but it really simplifies it into 2 smaller things. How many ways are there for me to pick Lori? There's only one Lori Hales. Okay, and now we want to pick 3 others. So we want 3 others out of how many others? 21. So does order matter? Don't think so. That's how many ways there are of doing this, but notice this is a probability question. If this is probability, that means we're taking part over total. So it ends up that we're just going to have 21 choose 3 over 22 choose 4. 21 choose 3 over 22 choose 4. You should just be able to type that in. Try it out. Okay, make sure you know how to use your calculator. But that's 0.1818 about. Part C says find the probability that Hales will not be downsized. Okay. Now, this illustrates something that comes up kind of a lot. A lot of the times there are 2 ways to do the problem. Either you calculate directly, or you can do it indirectly, which means find what you don't want and subtract that. All right, so think about this situation. If I said the probability that I'm wearing a blue shirt on any given day is 0.8, you should be able to tell me the probability that I'm not going to wear a blue shirt on any given day. What's that? 0.2. All you did was 1 minus 0.8, right? You can either tell me directly, or you can subtract from 1 and kind of go in the back door. All right, so in this problem, part C, there are 2 different ways of doing it, and I think the back door way is probably easier. We just found the probability that Lori Hale is going to be downsized. So how would we find the probability that she's not downsized? Exactly. 1 minus 0.1818. 1 minus 0.1818 is 0.8182. That's your answer. All right. Now, that's kind of the indirect way. And I think that's the best way of doing the problem. But let's think about the direct way. All right. So the direct way, we're trying to pick not Lori. But what that means is we're picking 4 others. Okay. I didn't mean to make that look like a division symbol. That's not divide. Okay. We're picking 4 others. So 4 others out of how many others? This is going to be 21 choose 4 out of a total of 22 choose 4. All right, that's how you would directly calculate this problem. So let's see if that works. 21 choose 4, those are the others, out of 22 choose 4, 0.8182. There it is. All right, so there's 2 different ways of doing this problem. Either you do it directly or you do it indirectly and subtract from 1. Next question. Number 3, a smartphone company ships phones to retailers, 12 in a package. Retailers have complained that many of the phones are broken when they arrive. The company decides to test the packages before shipping, randomly checking 3 phones from each package. If any of the 3 phones are broken, the package will not be shipped. Find the probability that a package containing 2 broken phones will be shipped. All right, so there's a lot going on in this problem, and it's kind of hard to understand. So first thing, imagine you're reading this question. All right, I think that the image almost makes it more confusing at first. All right, so reread the question if you need to try to understand it. Sometimes I have to read it multiple times. But you've got a box with 12 phones in it, right? And you're randomly going to check 3 of the phones. So that's kind of crucial. So they're randomly checking 3 phones, and I don't know if they're broken or not. I don't know. They're just going to randomly check. Who knows? All right. So if any of those 3 phones are broken, the package won't be shipped. Find the probability that a package containing 2 broken phones will be shipped. So that last sentence is kind of why I included this image. All right. So that last sentence says, all right, some package, there's 12 of them in there, and we know 2 of them are broken. But you don't really know which ones. You don't really know which ones of the phones are broken. And so that's why they're going to randomly check 3 of the phones. All right. So, I don't know. Are they going to check these 3? I don't know. We're just going to randomly check 3 phones. So if I checked those 3, it's going to ship, right? I mean, it's good. But to really nail it down what they're saying. Find the probability that a package containing 2 broken phones, okay, that's the picture here, will be shipped. Okay. So next, let's go back here. We're randomly selecting 3 phones. And if any of those 3 phones are broken, okay, I see one that's broken, we're not shipping this package. All right. So this is confusing, but when it says will be shipped, the only way we're going to ship is if we randomly select 3 of the good phones. Okay. So it's hard to understand this problem, but we're randomly selecting 3 phones, but we gotta accidentally or luckily or unluckily select 3 out of the good ones. Okay. So probability of shipping. Okay. Think about what we have to do. What we have to do is we're going to select 3 good phones. All right, and you can include or understand that that implies and select 0 broken if you want. But it turns out since that's 0, it doesn't really matter. Okay, that's what we're trying to do, right? We want to select 3 good ones and 0 broken ones. So 3 good ones out of how many good ones? So yeah, there are 10 good ones. We need to select 3 of the good ones out of that. Order doesn't matter. Okay. And I guess you could say 0 broken ones out of the 2 broken ones. I like writing it that way because it kind of does a good job of highlighting how many total there are. Well, we want to select 3 total phones out of the 12 total phones. We're picking 3 phones. All 3 of them have to be good ones. And so that's what this is going to be. Now, you should know 2 choose 0. What is 2 choose 0? 2 choose 0 is 1. And so that's why that doesn't really even need to be there. It's going to be 10 choose 3 over 12 choose 3. 0.5455. 0.5455. That is the probability that this package will ship, right? So an extra question I could ask is, what then is the probability that this package does not ship? Couldn't we just say 1 minus that? That happens every once in a while. We found the probability that this happens. We want to know the probability that this does not happen, so just 1 minus. So 1 minus 0.5455, 4545. Now understand, that's not part of the question. That's something else. I didn't ask you that. I asked you this. Probability that it ships. Okay, moving on. Number 4. In a common form of poker, 5 cards are dealt from a deck of 52 cards. All right, so this is a common probability question. You've got 5 cards dealt from 52 cards. How many different hands are possible? Well, how many? We want 5. We want a group from a group. We want 5 out of 52. And the order that I get those cards doesn't really matter. Okay? If I get a king and then a queen, who cares if it's reversed and you get a queen then a king? Doesn't matter. 52 choose 5. This number happens all the time in probability. 259 8960. That's the number of different possible 5-card hands. Part B says, what's the probability of dealing 5 hearts? 5 hearts. So now we're talking about a probability question. We talk about a group out of a group. I want 5 hearts out of how many hearts? 13, right? Order doesn't matter. Who cares which one comes first? Now, if you want, you can say, and I want 0 of the other cards. But 39 choose 0 is just 1, and so that doesn't really affect the math of this problem. But I do like what this shows me because that shows me 52 cards and I'm picking 5. It breaks it down specifically. 5 of them are hearts and 0 of them are something else. So par over total, the total is just going to be 52 choose 5. I want 5 cards total out of 52 cards total. So since 39 choose 0 is 1, I'm not going to include that in my calculator presses. I'll just go 13 choose 5 divided by 52 choose 5. 0.00495. Now, normally I like 4 decimal places, but I'll do more than 4 sometimes if I feel like 4 is not enough to really show the numbers well. So I'm going to use 0.00495 right there. Okay. Probability of dealing 5 hearts. Part C. I want to write small here. I didn't give you a whole lot of room. What's the probability of dealing a flush of any suit? So we just did a heart flush, but a flush of any suit could be hearts, could be diamonds, could be clubs, could be spades, right? So anybody know how to find this answer quickly? Yeah, the answer we just had times 4, right? That's all it is. So if we didn't just do that problem, you would say something like, we need to choose a suit and we need to choose 5 values. And so choosing a suit, you'd say, well, there are 4 suits and I'm just going to choose one of them. Times 5 values out of 13 values. We're doing that. Okay. Of course, over your 52, choose 5. But that's going to do exactly what was just said. We're just taking 4 times that number we just got, 0.00495. So I've got that number in my calculator. Just take it times 4. 0.00198. Part D, what's the probability of dealing a full house of aces and eights? We talked about this in the last lesson, except last time it was a counting question. How many ways of doing this? Now it's a probability question. What's the probability of doing this? So be really specific, hyperliteral. We want 3 aces and 2 eights. That's what we're looking for. 3 aces and 2 eights. So let's think about this here. Probability of aces and eights. All right. It's a group from a group. I want 3 aces out of 4 aces, right? So 4 choose 3, order doesn't matter. And I want 2 eights out of 4 eights. That's another combination problem. 4 choose 2. So on the bottom, it's your total, and there's your number again, 52 choose 5. I want 5 cards out of the total of 52 cards. 4 choose 3 times 4 choose 2 over 52 choose 5. Now you might know 4 choose 3 is 4 and 4 choose 2 is 6. So it's going to end up being 24 over 52 choose 5. Or I suppose you could just type it in. 4 choose 3 times 4 choose 2 divided by 52 choose 5. Either way, I see 5 zeros, and then we'll call that 923. Part E, hardest one yet. What's the probability of dealing any full house? So we just did a full house, one specific one, but now it says, what about any full house? And this is a lot more complicated than just saying times 4 or times 13 or something like that. You got to really, really nail it down what they're talking about. All right. And so those of you who know about cards have a little bit of an advantage here. If you don't know what a full house is 3 of one kind and 2 of another kind. All right. So let's think about it. It could be like 3 queens and 2 threes. But it could be like 3 sevens and 2 aces, right? Any full house is going to look something like that. It's going to look something like that. And so If I'm going to nail this down, I'm going to try to be really, really, really super specific. Visualize if you're dealing out cards, okay? If you're cheating for your friend or trying to deal them out to yourself and you're dealing yourself a full house, you have a couple of decisions to make, okay? And the first decision to make is what value of card do you want to give yourself 3 of? All right? So how many values are there? How many values of cards are there? There's 2, there's 3, there's 4, there's 5. There's 13 values. You should know that. All right. So let's nail it down first. I'm going to choose value and hang on. I'm going to scoot this over here. Oops. I'm going to choose a value, and once I choose queens, once I know I'm going to deal myself queens, then I have to figure out which queens I want to get. Do I want hearts, diamonds, and spades? Do I want clubs, spades, and hearts? I'm dealing out. I'm going to choose 3 suits. Got to choose a value, and then you've got to choose the suits. And so, how many values are there? 13. I'm going to choose one of those values. And choose 3 suits. Out of the 4 suits, there are 4 suits. I'm going to choose 3 of them. That's how I'm going to get 3 queens or 3 jacks or 3 eights or whatever. Okay, but I've got another decision to make. Let's say you dealt out 3 queens. Now you have to choose another value. Choose a second value. So, and choose second value. How many ways are there of choosing that second value now? There are only 12 now. So we can say 12, choose one. And after I choose that value, let's say I choose I'm going to give 4s. Now I have to choose which 2 of the 4s, right? Maybe I'll give diamonds and hearts. Okay, so and choose 2 suits. So times 4, choose 2. That's hyper literal. That's exactly what I'm trying to do here, is just be super duper specific. Okay, that's how I'm going to calculate this. Now, since it's probability, the total, I just want 5 out of my 52 cards again. So that's the easy part. So anyway, if you are looking for shortcuts, 13 choose 1, you should know that's 13. 4 choose 3 is 4. 12 choose 1 is 12. 4 choose 2 is 6. Maybe it'd be faster to just do that part in my head. I'm going to go 13 times 4 times 12 times 6. And that's my numerator, 3744. So when we did this question before, or if we had done this question before, how many full houses are there? 3744. All right. But I don't want how many, I want probability. So this is going to be 3744 over 52 choose 5, which was 259,890. We end up getting 0.00144. Again, the question always comes up, how many decimals do you want? And usually I like 4. I like 4 unless maybe 4 isn't descriptive enough. Maybe throw on 5 or 6 or whatever you think is descriptive enough. Now, I want to do this problem again, but in a slightly higher level way. All right, just slightly. So a little bit better way maybe of doing this problem is to understand when you're picking a full house, when you're cheating and dealing out that full house, you got to understand that queens, 3 queens and 2 3s is different than 2 queens and 3 threes, right? That's a different hand. One of those is better than the other one. 3 queens is better than 2 queens. All right. So anyway, another way of doing this problem is thinking again about what we did. How we're picking this is we've got to pick 2 different values. So maybe before I start, I already know the 2 values I want. I want aces and eights. Okay. But so you're picking 2 values. You're picking 2 different values. So you could say, all right, out of the 13 values, I want 2 of them, right? But order matters because 3 queens is different than 2 queens. And so in this case, I'm picking 2 of those 13 values, but putting them in order. 3 queens and 2 threes is different than the other way. All right. After you pick your 2 values, you just say, okay, the first value, I know there's 4 of them, and I'm going to pick 3 of those suits, maybe hearts, diamonds, and clubs. All right. And my other value is, well, there are 4 of them, and I only want 2 of them. Now, I want you to look at what we already did before, because what I just wrote down is the same thing as what I wrote before. Obviously, you can see the 4 choose 3 and the 4 choose 2 are the same. But remember what a permutation is. When we talk about a permutation, it's part of a factorial. And in this case, that says 13 times 12. 13 times 12 is exactly what we're doing right here. All right. And so this is a little bit higher level of thinking. If you can say, I want 2 of them, I'm going to put them in order. It's really the same thing, though. I think people that can think about it in this way have a little bit of an advantage on some of the harder questions, even though it's going to take you to the same place. Let's move on. The following 7 Scrabble tiles remain in the bag. How many 4-letter words can be made from the 7 letters? So 4-letter words, it doesn't necessarily have to be a word that's in the dictionary. They're calling anything with 4 letters in it, like W-O-G-M. They're calling that a word. Anything with 4 letters in it, that's a word. So you pick out four of those letters, throw them on the table, that's a word. All right. So how many 4-letter words can be made from the 7 letters? So how many? I'm reaching in that bag and I'm pulling 4 letters out. It's a group from a group. Okay. It's a group from a group. I've got 7 letters showing 1, 2, 3, 4, 5, 6, 7, and I'm picking out 4. And I'm spelling a word. And so does order matter or not? Well, that word is different than that word. And so yes, order matters in this case. That's a permutation. This is a 7p4. 7p4 is 840. Not probability, just counting. How many? Part B says 4 tiles are drawn from the bag, one after another without replacement. What's the probability that the letters W, I, N, G are drawn in that order? So, basically you're trying to spell wing, right? You're trying to spell wing. And there's only one way of spelling that word. It has to be pull out a W first, a I second, N third, a G fourth. It has to be in that order, okay? Has to be in that order. So it's just 1 out of the total. It's 1 out of 840. .00119. Part C, 4 tiles are drawn from the bag, one after another without replacement. What is the probability that the letters W, I, N, and G are drawn in any order? So anything, any order. So, I guess it's kind of hard to think of this as a group from a group problem because you are drawing them one at a time. And so if I go back up to part A, if you think about it, there were 7 ways of pulling the first one, and then 6, and then 5, and then 4. I mean, you can think of that as a blanks problem. Maybe that's better, okay? But since a permutation is part of a factorial, I'm doing the exact same thing. So in part C, what is the probability that W, I, N, G are drawn in any order? We've got those 4 letters, and so I have to draw one of those 4 letters, and then 3, and then 2, and then 1. I'm trying to draw one of them and then the other and then another, whatever. There's 4 ways to pick one of them, 3 ways to pick the next, and so on. So 4 times 3 times 2 times 1. You can look at that as a factorial, or you can look at it as a permutation. Out of those 4 letters, I'm picking 4 and putting them in order. Out of 7 times 6 times 5 times 4 total ways, or 7p4. It's 4p4 over 7p4. About 0.0286. Part D, 4 tiles are drawn from the bag, one after another with replacement. What's the probability the letters W, I, and G are drawn in that order? So this is a little bit different because now they're saying with replacement. So you pull out a letter and you put it back. You pull out a letter and you put it back, right? So we can still do part over total. There's only one way of spelling wing. It has to come in that order. W, then I, then N, then G. It has to be. But the total is going to be different this time. Because you're pulling out a letter. How many ways to pull that first letter? 7. And you put it back. How many ways to pull out that second letter? Also 7. Put it back. Third, 7. Put it back. Fourth, 7. This is going to end up being not a permutation, but just 7 times 7 times 7 times 7. You've got 1 over 7 to the 4th power. Zero, 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 416. Number 6. Find the probability that at least 2 of 28 people in a room have the same birthday. All right, this is an interesting question. It comes up every now and again. But probability that at least 2 of 28 people in a room have the same birthday. How many are in this room? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 2, 4, 6, 7. We've got 27 in this room, so it's a pretty similar type deal. Would you expect at least 2 of us to have the same birthday in this room? Probably not. What do you think the probability of at least 2 of us having the same birthday in this room? Just give me a number between 0 and 100. Okay, so like less than a 1% chance. Okay, good guess. Anybody else? I guess higher than that, maybe. Okay, well, let's do 28. Here's what we have to do here. Okay, when they say at least 2, what that means that 2 are the same, or 3 are the same, or 4 are the same, or all the way up to 28 being the same. Now that's not very likely, right? The probability that everybody in this room has the exact same birthday is not very likely. But in this problem, what happens is you end up having to add a whole bunch of probabilities together. And the result of adding all those probabilities makes this answer a lot higher than you would expect. Okay? So here's what I would do. Okay? We'll go back to these problems have 2 different ways of doing it. Either you could calculate this probability directly by finding each one of those individual pieces and add them together, or you could calculate this answer indirectly by finding what you don't want and subtracting that from 1. That's going to be much faster in this case. So when they talk about at least 2 people have the same birthday, the only case that they're not talking about is if they're all different. Okay? Let's think about everybody in here has a different birthday. So let's say all different. That's not what they're talking about, right? We can calculate this probability indirectly by saying let's just take that out. Let's take 1 minus the probability that they're all different. So we're going to do 1 minus the probability that 0 people have the same birthday. Now, one person having the same birthday doesn't make any sense. That doesn't mean anything. But the probability that nobody matches. 0 people have the same birthday. Okay? So for 0 people to have the same birthday, they are all different. So what happens there is this. In order for everybody in this room to have a different birthday, we know there are 365 days in the year, and we have to have like 28 different ones of those. Okay, 28 different ones of those. So it's a group out of a group. There are going to be 28 different days out of the 365. All right, so it's a 3, 6, 5, and a group of 28 in this example. And in this example, order matters because if yours is January 1st and yours is February 1st, if I switch those around, that'd be different. Okay, so order matters here. So I'm going to have 1 minus that. That's the part. Now I need the total. All right, notice where the denominator is. The 1 is not in the top of the fraction. It's a different fraction. Okay, so think about if I'm guessing your birthday. If I tried to guess your birthday, how many choices would I have to guess from? Right, 365. I'd have 365 days to guess for his. Now, if I try to guess yours, okay, I'd still have 365 choices. If I'm guessing yours, I'd have 365 days to choose from, and yours same, and yours same, and yours same. I'm trying to guess everybody's birthday. I have 365 days to choose from, right? So basically, what happens is 365, 365, 365, 365, 365. It's 365 to the 28th power. These are really big numbers. Your calculator might not be able to handle it. Okay? But that's going to give me the answer. That's going to say this is how many, this is how many ways of making 28 different birthdays. And 1 minus that is going to give me 2 same or 3 same or 4 same. So check it out. Okay, I'm going to do the fraction part first. 365 and a permutation of 28 divided by 365 to the 28th power. 0.3455. 3455. So 0.3455. What that means is there's a 35% chance that everybody has a different birthday. But that's not what I want. I want the opposite of that. I want to add up all of these things. And so really I need to subtract that from 1. 1 minus 0.3455 is 0.6545. That's the answer to this problem. I think that's really almost unbelievable. We've got 28 people in this room. There's a 65% chance that at least 2 people have matching birthdays. Okay, does anybody know each other's birthdays? Sometimes you guys know each other's birthdays. Well, I've got the same as so-and-so. But if we went through our birthdays, there's a really, really good chance. There's better than a coin flip chance of at least 2 of us sharing a birthday. I think that's kind of cool. Now, I did a spreadsheet, and this spreadsheet kind of shows what happens at different numbers. But if there are, let's see, where were we? What do we have? 20. We just found 28. 28. We just found that the probability of a match is 65% at 28. I think our room has 63%. Our room only has 27 people, so it's a 63% chance in this room. All right. If you go back to 23 people in a room, if there are 23 people in a room, it's a coin flip. 50-50 says there is a match of birthdays. Okay. But check out how quickly these numbers grow. If you go to 50 people in a room, there's a 97% chance that there's going to be a match. Okay, kind of hard to believe. And as soon as you get to 57, it's a 99% match. And of course, if there are 365 people in a room, you would expect a match, but it goes up to, I mean, it goes up real high real quick. If there are, these numbers are kind of big, so Excel like can't handle the calculation anymore at 120. But as soon as you get 120 people in a room, it's a 99.9999999.7% chance that there's going to be a match. I think that's pretty interesting. Okay, let's move on. 7. 5 apples, 6 bananas, and 7 lemons are sitting on a table. How many ways are there to line up the fruit? It's hard to recognize this question, but this is the Mississippi question. All right, I like to look at it like this. 5 apples, indistinguishable. 6 bananas, indistinguishable. 7 lemons, indistinguishable. Okay. If those things were all different, think about the Mississippi question. If all of those were different and you could tell this one was green and this one was red and this one was yellow and, you know, whatever, then it would be, what is that? 18 factorial. If all of those things were different, it would just be 18 factorial. But because you can't tell a difference between the apples and the bananas and the lemons, we're going to divide off the number of ways of shuffling the apples and shuffling the bananas and shuffling the lemons. That is the Mississippi question right there. How many ways? Ooh, I don't think that's going to work. I think I need to put parentheses. $14 million or so. Okay, last one. Find the probability that all the fruit of the same kind are placed together. I'm going to finish this up even if the bell rings. Basically, you'd want it to be 1 over, but this problem that I just did makes apples first, bananas second, and lemons next. That's not the only way of doing it. You could shuffle these. Could be apples, lemons, bananas, bananas, apples, lemons, bananas, lemons, apples, lemons, apples, bananas, lemons, bananas, apples. Basically, there are 6 different ways of shuffling the fruit. Okay, so this answer is going to be 6 over 14,702,688.